How many people here works with core CLR? So I see a few. On the desktop CLR? Okay. On other languages, Python. I don't see anyone. C++? Okay, good. Well, I think we're starting. Are you having good fun on NDC? Yep. You like it? Good. I'm here to disappoint you. Okay. For those that do not know me, I have been working on performance for more than 10 years. Like I have used like every single CPU kind of stuff that you can think about, from very, very low power stuff to high powers GPU. So if you have any question outside from what I'm going to talk about today, which is in a sense C# only, but most of these techniques work on other languages. That's why I'm asking. This kind of stuff, it's pretty interesting for me. So just get me around the corner and just ask me whatever you want. Today, what we're going to talk about is how you deal with the cases when you actually need to go on high performance. Because let's face it, most of the time, we just don't care. As long as it works, as long as it's in budget, we're fine. So let's say that on Monday, your boss comes and says, hey, you know, we have this new client, and we actually have to be able to deal with 20 billion operations per day. I'm going to wait a little bit so you actually sync on that number, which looks like this. How many of you have had the luck to actually deal with this kind of stuff? Okay, we have a few. So big, probably on the 3 or 5 companies that actually have to deal with such amount of requests. So let's say this is a big number. This is something that it's, for most uses and purposes, untractable to your mind. So let's start to work around this a little bit. So we're talking about 20 billion operations. So if we look at like, okay, let's assume that this is uniformly distributed, which usually is not. But let's assume for a bit. That's around 800 million. Yeah, more or less, give or take. But you know where this is going, so we are going to try to narrow this down as much as possible. So on 60 minutes, how much we have to deal with? 30 million, it doesn't look that bad. At least not as bad as the 20 billion when you started. When we go to a minute, this is actually a tractable number. This is a number that you can get your mind around, and you can think of it. So what would you typically do? If you have to deal with this, you will just go and spin up a cluster, typical stuff. You go, you build your Kubernetes, you deploy, and you're done. Because this is roughly 5K, 6K operations per node, which is, with today's tools, totally doable. The thing is that for most state of the software today, even though there have been a lot of strides, that's why I asked first if anyone have been using core CLR, because the system tax of actually serving requests on core CLR and the new ASP.NET has really go down, but real hard. At some point, like 5 years ago, with your highest end server, this actually was the task of MVC. You were not going to go even higher than this because that was about it, just to serve static stuff. So typically, this is how we usually solve it in the usual industry. Like, we just keep spinning stuff. Like, because this is a number that is simple. If you have 150 operations per node, it looks fine. I know many, many, many enterprise applications that are even in numbers lower than 10. and they are supposed to be high performance. So just to give you a sense of what the very first number that we log, like 5K operations per node means, is roughly around 5 milliseconds per operation per second per node. Game developers have been working with even worse budgets to actually make games. So this is actually quite high. Everything that we are doing today has been solved in one case and another, had to be solved to actually make games. So if we are not able to solve this kind of problem with like our bare hands, we're screwed, really. So when optimizing, it's like you can have like these 3 levels. In one level, you have like, okay, this is piece of cake. This is something that junior developer can knock out in a weekend. If you're not able to achieve 600 requests per second per node in a weekend, you are doing it wrong. But then the typical enterprise software and most like 90%, or if we use Pareto, the 80% software, it's around this kind of this level. You have operations that are really time sensitive, but most of them are not. So if you deal with those and you are able to achieve a sustained 6,000 requests per second per node, you are like in a very good place because you are not burning money, which is good. And you're also able to serve with a less than 5 millisecond latency if you are like right to the server. But I particularly work on a particular field, which is database engine design. If you have to serve this number, I have to live in this number. Because you're not going to like ask me for a record. You're probably going to ask me for like, oh yes, this is the user and this is the other thing, and now give me the profile, and now, well, so probably I have to serve around 4 to 7 requests before you can actually finish your operation. So this is the kind of level that is baseline for anyone working in the database industry. And you actually have to go higher than this. But you can think about this from your own perspective, not from the database perspective, but for your own system perspective. And you can think of it like there's metrics that we know it's like that. If you are in the, if your target is 1 second of latency, we are not talking about throughput here, we are talking about latency. If you're in 1 second, you can knock anything in a weekend that can do stuff in sub-second, okay? But when you go lower, that you have to keep a budget of 100, then things start to add up. The complexity starts to add up pretty fast. So today's talk, this is one of the important things that about today's talk. We are not going to talk about how to make performance is a big field, okay? There are like things that you can actually go to the books, and it's there. If you go around interrupt calls, you know that allocations are the major source of performance issues, like major. If you have a software that is misbehaving, the very first thing that you are going to look at is allocations, period. This is like the sanity check. This list is like the sanity checks. But I want to watch at 2 in particular, which is allocations are a major source of performance issues, which is something that we know already, but also a tidbit that is probably not so known in the community, which is value types are subject to a special sets of optimizations by the chassis type compiler. This is important. This is what the entire talk is going to be around after we end like the introduction stuff. So there's other interesting things like that happen at the moment of emitting code that the just-in-time compiler does. And one of the most important for this is that it's able to constant propagate stuff. So if you have a constant and the just-in-time say, hey, this is a constant. Now it can propagate it up over the stack as long as there's no a method call. There's no a method call. On the other side, it can eliminate code. If the condition is false and you're not going to enter it because you left it there for like debug purposes, it's not going to end in release code because it's going to be eliminated. So if you're serious about performance, my recommendation is get these 2 books. You don't need anything more than that. The first one is a real good book about the specifics of how to actually do benchmarking, because if you're measuring wrong, you are taking the wrong decisions, period. This one, Product.NET Benchmarking from Andrea Kinshin, is going to be available in September. I know it's good because I read the draft. The other one is about dealing with memory, like understanding the memory model of .NET and actually work around from it. So that one is already available. So when you start working with performance, it's pretty easy to just go for the very small things and not figure out that, hey, there's actually a good in here. So let's not go for the tree, let's go for the big thing. So we devised a way to actually characterize internally what kind of problem we are dealing about. Think about the Pareto. You can take the Pareto distribution. 80-20, which is like the typical how you think about the Pareto distribution. So let's say that you have the 80-20. Now, square it. This means that if you think about it, if 80% at the first level, 80% of resources consume 20% of the code, is caused by 20% of the code. Now, if you square it, essentially what you have is like that 4% of the code actually is responsible for 60% of the resources. And if you do it again, you go cubic. Now, 0.8% of the code consumes half the resources. And this is not a rule. This is something that we found in practice. I deal with the 0.8, usually, because it's too costly to actually go to the 4 and to the 20. And I'm going to show you why. But the idea here is that if you say, this is a Pareto problem, I know that we are talking about next major version, period. If this is a Pareto square, then I'm talking something that probably it's a high-risk task. It's something that you would not do like in a weekend. But if I talk about this is a Pareto cubic thing, then okay, this makes sense. I probably can do this. I can figure out how to make it work in a few weeks. But this is because we have been in the process of optimizing for years. So essentially, I'm looking for the 1%. Like having a micro-optimization level, which is cubic, is essentially, I'm looking for 1%, 2%. If I get a 10%, it's like major. So the idea here, when you go up in the scale, what you are looking actually is typically the network, I/O, architecture, big algorithmic stuff. Like if you're using a n to the fourth algorithm, instead you could do that in linear or sublinear. Like big stuff. Like if you change this, you are looking for more than 20x performance improvement. If not, you are not going to do it, unless obviously you are just starting with the process, in which case it's always easier to go on top because it's where the actual payoff will be. It's not uncommon if you go to a new software that hasn't been optimized before. If you go, where I go hunting in if a new clients come in, where I go hunting there. Why? Because probably it's highly probable that I can find stuff that I can still fix on this level. that is not high cost, and it have an insane performance improvement. We are talking that a fix there can get you 60x, 70x. I have seen on the wild 120x. That kind of improvement, if you're selling, for instance, by course, is actually gonna kill your business model. So the second level is where you're dealing with like small variations and the algorithmic time. So probably you are not moving from the, you probably are going to get like, you have an N and you go sublinear, or even between the sublinears, not all sublinears are created equal. So this is what the kind of stuff that we learn in complexity at the university. Like, oh yes, I have this big, huge, this beautiful algorithm that can do like sublinear stuff. But hey, my size, my world is so small that even the linear one is going to be faster. And then it's the world the world of micro-optimization. That's where the voodoo happens. This is what this talk is about. So the very first thing that you have to know from the start is if you have to micro-optimize, make sure there's no option because it's a one-way road. When you start in the micro-optimization, your code is gonna start looking way differently to what it looked before. And it also means that you have to be very careful how you change it a long time. So the people that is allowed to touch that code, it's gonna get reduced pretty fast to the real senior stuff. So this is like last resort. It's like I don't have any other way, so I go this road. But because you're here to see something that you can find in books, let's talk about this. So this is a true story. Everything that I'm going to tell you from now on is based on a particular of the work that we did for a particular product. So everything is time. I'm going to start introduction where we were and where we needed to go. So obviously, what I would do from the get-go is let's go hunt for the bottlenecks. So we started with RavenDB Bottlenecks at the major version 2. So we figured out, hey, you know, after some optimizing and figuring out, we actually figured out, okay, the single write log and the lack of batching operations, which is architectural stuff. This is something that you are not able to change like from, even in a few months. This is major stuff. This is stuff that if you have to deal with it, you have to create an entire new major version for it. Also, the interrupt cost. There was like this amount of decisions that were made on the initial, on the planning style, on the planning moment of the product. You end up there. So this is not something, any of these problems is something that you can fix on 2.0. So you have to start thinking, okay, how do I deal with all this? So essentially, this is what we did. We figured out, hey, you know, we don't have batching operations. Okay, we built like an entire engine that is able to batch operations. We have to deal with the interrupt cost. We built an entire database storage built on C# just to avoid the interrupt. The hashing, we implemented like, we have a huge farm of very specific hashing functions specifically for each use. And all of them, instead of going to the optimized C++ code, they are just built entirely in C# to avoid all the interrupt. So we end up in 3.0. And in 3.0, hey, newsflash, new bottlenecks. So it's not like, okay, yes, I get rid of these ones, but now those ones become like huge. So just to give you an idea, just dealing with those kind, we just get rid of 10x. Which means that when you needed full computers, now you can do the same with half. So when we started 4.0, now another major version to actually deal with all the other stuff, we did a lot of stuff just to get rid of those bottlenecks. And the most interesting thing here is that we actually had to go unmanaged. We have to deal with the memory itself. And when you start on that road is when I say, it's an only way. So if you go there, you are not coming back, period. So we went by the book. This is the kind of thing that if you're optimizing, you will do, period. So we decided to tackle these three, just these three. The entire Mayor version was about tackling this. We ended up doing some work on the others, but was about these three. This is the Mayor thing that you are going to do. Okay, we took 2 years. It's not like something that you can do. We are looking forward 2 years to actually build a Mayor version. So we started with a very simple assumption: we set request. Hey, what application doesn't do that? It's typical. So So the interesting thing about requests is they start and they end. They're stateless, kind of. So the interesting thing is when you start to look into these requests, you figure out, hey, string allocations dominate, and dominate big. Like, we are talking about gigabytes per minute. So when you look at, and you start disaggregating all this, you figure out, okay, collections like are a huge issue. You look at generation, gen 0 reclaimable. So you build this object and you return it. That's cost. Don't get me started with async. Async is cool. Yeah, it's cool. Its performance is real bad. If you are in sensitive code, getting out from the async machinery is like the best thing that you can do. It's like you are going to get a boost, huge one. Also, you have to be very careful with the lambda capture context. We have lambdas everywhere because lambdas are cool. Yeah, but the context, when you have to capture the context, you're allocating. And if you're allocating like in a loop, 1 million operations in a minute, that adds up pretty fast. So we decided, okay, we are going to get rid of allocations. We are going to we are going to create our own string representation, because we were already dealing with unmanaged stuff. So we couldn't fake it. Now you have span. Still, if you're dealing with unmanaged stuff, span is not that good. So the thing is, we went all this road back in 2015 when span didn't exist anymore. But what I'm going to show you is how you can build span-like abstractions in raw C# without needing the just-in-time optimizations specifically. So let's think about what we created at the time, which was the ByteString. If you look at the raw implementation of a span, it looks more on a string. It more or less looks like this. You have some flags in our case because we needed to write down some stuff about that particular string. You have the length, you have your pointer, and you have the actual size. Okay, so the length of the string and the size of the memory that it's backing it up. This is very specific to our use case, which is we reserve an amount of memory, and if it shrinks, we don't go creating and getting new memory for it. So obviously this sounds familiar, because if you look at it, this is a span, which is essentially a pointer and its length. But the problem is that you cannot do this. At least not legally. This is not legal C#. So the problem with this is you can see the magic word in there, which is a struct. That's 36 bytes. If on every method call that I do, I have to copy 36 bytes, that's huge, right? It adds up pretty fast. Let's do the math. 1 million of those, 35 bytes, that means 35 megabytes per million calls, which is big. And that's assuming a single parameter. But you know, anyone that comes from the C++ or C background knows how to fix this. Actually, we are told how to fix this in university, which is there's no problem in computer science that can be solved if we don't add another level of indirection. The problem is what kind of indirection that you are adding. Okay, some of them are intractable. So essentially what we did was this. Okay, we have a backing storage. We have like this huge array of memory. And this is a pointer to that particular case. So the question is, how much do you think this cost? Anyone to gamble? How much? Do I get that 16 bytes here? No, no 16. Do I get an 8? Yes, 8 bytes. So this pointer is the size of an integer. And because this pointer is the size of an integer, we can do a very simple exercise, which is, hey, how much does passing a ByteString as a parameter cost? So we essentially did this. Sorry, an integer, no, a long. So we are doing something like this. We are comparing it with long, which is essentially has the same size. We wanted to know if that is the same thing. So essentially, we took the very roots of the ByteString, which is essentially the backing store, which is a pointer, and we execute this. Let's start with the long. This is how a long call looks like. So essentially, you move the stack, you move that to the RC, you move the location to the RCX, you call the using long, you move the results back to the RCX, you execute write line, data knob, I don't know where it comes from. You now work again with the stack, and then you return. This is your method call. Let's do the same thing for our pointer. Let's do the same thing for our ByteString. Now, we got the move, we got the call, we got the copy to the parameter list again. We got our call, and we got our result. We're coming back. So, anyone can guess which one is the ByteString? I don't know you, but I know that I can't. Why? Because of this. This is the only difference. So I think at this moment that now you're starting to understand and to know where this is going. But wait for it. Let's talk about an entirely different concept that comes from other languages, not C#, which is metaprogramming. For those that came from this C++ a C++ background, you have seen this kind of stuff before. Those are marker interfaces. You're saying, okay, this is a trait. You got an interface, and you build a struct out of that interface. So let's think about this. If we have a marker A, we know that we can call anything that is defined already in the interface. And if we got a marker J, we also can do the same thing. In this case, this also is an empty interface. But the interesting thing is that we can write something like this, where our method is going to take a type, which is actually an interface. But because the implementation of these guys is a struct, and I don't know if you remember from the very first slides, what happened with structs, with value types? They are subject to special optimizations. Because what it happens if we call this method, which is generic method marker A, 1, 0, what we actually get is something like this. And because, you remember from the second slide, which says code elimination. It just happened that if you are equaling one thing that is equal to the other thing, it goes out because it's true. So this is the only code that gets emitted. What happens if we do the other way around? If we say, okay, this is marker J. We have a type, which is also, we know it's different. So now it happens like this. So this is the code emitted. But, why metaprogramming is good? Because we have been using it successfully for years. So it's not something that you say, okay, no, this is new stuff. No, this has been here for 20 years. It's just that we didn't have the facilities to actually use it. So why we would use these kind of facilities? Because we can get rid of virtual calls, which are absurdly expensive. Because we can tailor our algorithms just for the case they were being called for. So if I know this algorithm, this location is going to be used in this way, I can instruct the runtime. This is how I want this algorithm to work. How you would solve this today? You just go and write 2 methods. And what happened when you have to do that for like 10 different use cases? Yeah, it's a maintenance nightmare. If there's an error, you had to actually go to all 10 places to figure it out. So also, if you can exploit the knowledge of things that you know are constant now. They may not be constant normally, but let's say, okay, your page size. For us, our page size is like, this is a constant. But it can be a constant on certain conditions and not on others. So we can actually play with this and still use the same code. And also, it allows us to avoid invariant conditionals, which also are very good at the CPU level. That's your real runtime, where the real meat happens. So and this is important, there's no better branch predictor than do not having to predict. It doesn't matter how good you are to actually figuring out, hey, yeah, in this loop, we are going always through this particular. You still have to check. And you still have to go there. In this way, you don't. It's just you emitted the actual code that you are needed to execute linearly. So let's talk about, this is what we are going to talk about is the building blocks to actual metaprogramming on C#. This is the building blocks. Then you have to design on top of it. You have to build your library thinking that you're going to use them in this way. That's why I said, when you go the road of micro-optimization, there's no coming back. So let's think about it. Anyone that hasn't used a object pool before? Anyone? Everybody used the object pool then. Okay, so essentially an object pool is, allocations are a big problem. So we put all these allocations, and whenever an object gets created, instead of like throwing it away for the garbage collector to reclaim, I just put it somewhere else. So if someone needs them, they just can go and try to get it from there first. So let's say that this is your object pool. The typical type of the object that you're going to store there is T. What the hell are the other two? We are saying, hey, what's the lifetime? This is a policy. The typical policy that you will find on eviction algorithms, for instance. This is a policy. Hey, what's the lifetime look like for this object? Or, hey, this is going to be run on a thread-aware, on threaded coded, or it is going to be run away on single-threaded stuff. This is the kind of markers that we are in there. So you're going to actually have a single object pool where you can actually say, oh, no, this is going to run on a thread, on a multi-threaded space, so, okay, let's pay for the cost. Oh, no, this is not going to be run. This is going to be single-threaded. Okay, why I'm going to pay for all the synchronization that can happen? We don't care. So let's think about this. This is our pool. This is our pool. We have an object pool T, and we also have like this default implementation, which is like, okay, this is an allocator. This is a lambda specifically. And we have a non-thread aware behavior because, okay, we are running this on single thread. You see there the funct of T factory? This is the factory. This is what we use to actually create the object. Because if you go in reflection, I can tell you now it's going to be bad. So the interesting thing about this is this. This is an object that doesn't exist. This is an object that we decided that it has to exist. So as you see, that object actually is implemented iObject lifecycle. What it does? Hey, it does new. Nothing else. But there's something interesting here. Hey, this is not a class. This is a struct. This is different. This is treated different by the just-in-time compiler. So let's see what's the difference in here. Let's say, okay, we are going to run the factory, which is our usual. We are going to send over a lambda expression, and we are going to use the one with the function allocator. You can see the numbers. We are talking half the cost. If you're allocating 10 objects, it doesn't matter. But if you are allocating 1 billion in a minute, that's half the time. So in this case, the difference, the actual difference is 27 assembler instructions. And with 27 assembler instructions, you actually got half the time. Because those instructions are the exact instructions and no more that you need for this specific task. So let's talk about another use case. This is, anyone have been using dictionary before, right? It's like, if you're not using a dictionary, you haven't coded in C#. Well, dictionary are particularly bad when you have to define objects which are user-defined. Why? Because of compilers. So we built our fast dictionary that actually has other improvements, but let's focus on this particular thing, which is, we are going to bake in the types, the policy for the compiler. So just give me a struct here that implements iEquality compiler to actually call at the moment that I need to compare stuff. The usual dictionary is iEquality compiler to key. It's like I'm using the interface instead of our particular implementation. So how an equality compiler would look like? Let's say that we have an equality compiler for long equals and get hash code, asking the hash code from the long, which is not returning the same long. Important. You are going to kill your dictionary if you do so. So who can guess which is the slowest? Anyone I get a 1? Anyone wants to guess the 2? How about the 3? Yeah. Anyone of you have seen this talk before? So yes, we are talking here about 19 microseconds against the base implementation with using, so you can see that our dictionary is faster because of different design choices. But still, when you go specific, you can still have half the time, which means that even if you implement the dictionary as it is and bake in the third type, which is the compiler, you are probably going to get half the time. It doesn't matter how much the Microsoft implementation improves, you can still improve more because the cost of actually doing the comparison for a dictionary is high. So if you can emit the exact code for that comparison, it's always going to be better, period. Just to give you an idea, and because numbers, you can actually mess it. This is an idea of how different it is graphically. We are talking huge. So just to give you an idea, these are actual numbers. This is from an actual workload. You can actually look that try get value and the get hash code and they are equal from the dictionary are like absurd. And in this case, this is a worst case scenario because I actually had to call comparing line, which is a huge thing because the just-in-time compiler didn't want such a big method, so it actually forces me to actually call that method. It didn't honor the aggressive inline, which is also very important because I mentioned in very, very deep in those slides, compiler directives are hints. They are not requirements. So the just-in-time may say no. So this is on the wild stuff. This is like I got 3x improvement just doing this. If you are in the 1,000, that means that you are able to be 3,000. Your throughput has just tripled. If this is your problem. But let's go back to the actual primitives. Let's go back to what this talk is about is how do I craft code that uses this kind of techniques? How do I know that the code that I'm actually writing is accessing these kind of optimizations? Let's say that we have this policy, which is a simple one. It's eviction. You have seen it from any cache service. So in this case, I decided to just go very, 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 very simple and say, well, okay, well, you can never evict from here, or you can actually always evict from here. So this is a demonstration. So let's say that we have our cache, and we are going to clear the cache. What will happen if I cannot evict? Essentially, what it will happen here is let's look first at the code. We are going to ask, hey, can we evict from here? No. OK, we are not evicting. Can we evict? Yes. Is this type disposable? Then we are going to actually dispose the object. If not, we don't care. We just clear. So in this simplified algorithm, we can actually go and look what happens when we call it in different ways. So let's look at this. So we have an int that we are never going to evict. We have an object that we are always going to evict. We have a disposable struct that we are always going to evict. We have a non-disposable struct, because structs can also be disposable, that we are going to evict. We also have a class that we are always going to evict. And there's always a non-disposable class that we are going to. Did I miss anyone? I think no. I think this is the good matrix. Let me know if I miss anyone. OK, so now let's look at the interesting part, which is you actually go to the assembler code of the release build and look at it. This is what we get. Can anyone see any pattern? I will make it easy. So we have a combination of different types, but it just happened that, hey, there are 3 that are equal. What do they have in common? They are not structs. They are not value types. Because the runtime is not able, at least for now, and do not see it to be happening for at least a few years from now, is not able to figure out that these are different types of classes, everything gets collapsed to the same code. But hey, on the other side, we actually see different calls. So let's inspect how those codes look, how that code looks like. So we started from this. This is the int, and this is the never evict. So interesting thing about never evict is that it always returns false. You remember what happened with constants? They get propagated. And you remember what happened when something is false or true, so it's a constant. The code gets eliminated. So this is what is important to us, but it gets ended up looking like this. If we don't trust me, go to the assembler and you will see this. This is our 138 version. Let's look to our disposable stuff. And we don't always evict. So we know for sure. It doesn't matter what we put on the first one. If we always use never evict, we are going to end up with the same code, period. But in this case, this case is interesting because we know we are going from the top. And then we are going to end up in type of iDisposable is assignable from type of T, which I didn't use the shorthand version, which is type of T iDisposable? That's the shorthand version. So the interesting thing about here is, okay, well, yeah, we have our constant that we propagate on top. And we also have iDisposable type of T, where T is a struct. Okay? This is how we propagate. This is the end code. Anyone sees something fishy here? What about the else didn't go out? We cannot get rid of this branch so easily because for some reason, the just-in-time compiler doesn't figure out that those upper things is a constant. That's why going to the assembler is actually very important when you are writing this kind of code, because you can end up in these kind of situations. So we are going to say not today to this one. There's a way to get rid of this, but it's very complicated. But if we look at this is interesting. If we look at this, so we are essentially, if we write the other one that we are going to take the other, we are going to end on the same code, right? But when we look at the core, it says, hey, these are actually different. And you know why? Because the structs are different. Okay? So while this is interesting in its own self, it means that, hey, the just-in-time compiler is actually building it. It's actually building for the different structs, the different code for each one of those. So if I look at this and I see the type of iDisposable is assignable from type of T, and it's not getting rid of it, I don't know in your country where I come from, this is a bug. So yes, it's already reported. I already reported it. So you can actually go to GitHub and actually vote for it. So this is our first example. This is how you are actually doing code specialization. This is an example of actual code. This is code that is running live today if you're running RavenDB. What it does is says, okay, we have this LC for compression algorithm, which is running entirely on C#. Why? Because if you go for a version in C++ or something which is faster, it's not because of interrupt. This is actually as fast as the C# C++ version. And I can actually show that it's possible to actually write in C# so fast code that you can actually rival the hand-coded assembly version. So in this case, essentially what we are saying is, okay, yes, we have these markers that are going to optimize in different ways and to deal in different ways with the data that comes from the actual stream, of data stream. So if you are dealing with like a 16 version, we are going to execute that code. If you give me the 32 version, we are going to go to that code. And if none of those, we are going to throw an exception. So you will know that you're messing up with this. And only the very first part of this is going to be put in the actual assembly. It's going to be emitted. The other one is going to get discarded. Now let's go to a different building block. This is an entirely different. It's more or less the same thing, but you are actually doing it differently. What you are saying is, okay, yes, I have this I manage write buffer interface that has all these bunch of methods. So I create an struct for each. So I have an unmanaged stream buffer, and I have an unmanaged write buffer, which are entirely different. One is I have the entire memory at hand, and the other one is I have a streaming version of the memory at hand. You can actually say, yes, I can go manage to, yes, I can build a managed version too, if I want to. But the interesting thing about this is that this gets embedded into another sealed class. And because it gets embedded and because it is a struct, whenever you tell me, hey, you know, I want a bleedable writer that is able to write to a specific type of unmanaged write buffer, I'm going to emit a new bleedable writer for each particular type that you give me in. So whenever I call any method on this particular bleedable writer, I'm going to be guaranteed that the code generated for that class is going to be tailored for the specific struct. Stop here. This is important. Think about it for a minute. We are saying, hey, we have classes, and classes by the runtime, they don't get like, they get all put in the same place, right? But in here we are saying we are emitting, even for a class, different versions of it, tailored for each use that we want to. This is not a method. This is a class. So I can go and say, okay, I have this Façade for the object pool. And the way that I deal with the object pool inside, it's just no longer a question of how do I write? I have to write all the code for the different behaviors. No, I write a Façade, which is object pool. And I implement how each one of the operations is going to behave on the struct itself. So now, every time that I have a reference for this kind of class, what I have is an actual reference to an actual implementation that is implemented up to spec. This is an example. We use write number. Write number is different for each one of the implementations. And it's a very, very highly costly operation if you call it. Now, because we are using aggressive inlining and all that, the just-in-time actually get like a huge method when I do the writes and optimize the layout of the code based on that. So this is another block. This is an entirely different way of looking at the same thing. Think about this. What's a page in a database? A page is like a chunk of memory of a known size that also has a known header and all the different things that you wanted a page to have, okay? And we allocate pages like crazy because, hey, I can have pages like of 4K. So picture if you ask me for something that is like a megabyte. But the interesting thing here is that you can actually hide that complexity away because you can say, okay, this is a page. This is the actual pointer, which is an index to somewhere. And all the methods actually get calls from the backend store. But this doesn't have to be with unmanaged memory. You can have an array of objects. And instead of passing integers, you can actually pass something that is able to deal with all the complexity that you are dealing with, which becomes an index. So you can have an opaque reference to any internal structure that costs absolutely nothing. The actual runtime cost of this thing is passing along over the stack. So the question that you may be asking right now is, this is worth the trouble? Because I said it, if you are going this road, there's no going back, right? This is optimizing the JSON parser because, hey, we needed to optimize the JSON parser. And the problem was, okay, yes, we arrived to something that is pretty optimized, but we are not able now to deal with the bottlenecks like changing how parsing is done, or at the next level, which is, okay, we are dealing with this. We can change the actual algorithm behind the parsing because in the end, parsing is simple. It's an state machine. So in this case, we started. This is when I took all this, it was 3 weeks ago. It was actually 3 weeks ago. This was from the internal channel. Hey, we were here, now we're here. So in 2 weeks of applying these kind of optimizations, the bleedable writer was one of those. We went from, that's around 500 seconds, like 6 minutes or something, even a little bit more, to under 3 minutes. For a database, that's huge. I ingest JSON. But then, 1 week afterwards, we were already in almost sub 2 minutes. And the interesting thing is, we were trying, because you remember that part of the Pareto is like 0.8% of the code. Because I work in the 0.8 part of the code. I was optimizing something else. And this happened. Because in the end, I had to optimize some little routine that actually was used by the parser. The general offenders are always the same. When you're at that level of performance, and when you already fix the stuff at the first level, and you already fix the stuff at the second level, the general offenders are always the same. It's the very same. I can tell you like the 10 files that takes 80% of my time in a year. And I work always around those 10 files and its friends in a 500,000 software project. So it's 500,000 lines software project. So you get the idea. 10 files. That on the wilds means that I got a 6.6x improvement in between the release and a few weeks later in a patch release. So let's put all this together, because I think that all this may look like separated. Like this technique and that technique. Actually, the second level of this talk is actually what are the design tenets to actually design libraries based on metaprogramming concepts. So in this case, we're going to put it together to try to try it. We are allowed to specialize generic code for specific conditions. The STL of C++ is exactly about that. It's about tailoring your code emission specifically for the problem that you have to solve. Also, it allows us to create facades for types that we know we cannot fix the problem at this level because, okay, yes, I'm going to be everything depended on this thing. But what we can do is say, okay, we are building a zero-cost facade on top of this, and every color is going to tell me, so the only thing that I have to do is go to the color and see, okay, how do you want to use this? Oh, you want this to use this in this way and this way? Use this parameter. You go to the other color and say, oh, and you want to use this? So every single one is going to get what he asked for. The general layout of the code didn't change, but the underlying emitted assembly did change, and it's way faster. Because now it doesn't have to check, hey, I needed to do this or I needed to do that. No, that question is never there anymore. You just go, you just have only one path to go, which is doing the job that you were asked to do. So for anyone that comes from Rust, this is essentially the concept of traits or zero-cost abstractions. The same if you come from C++, it's templates. Templates, the important thing about templates, if you think about it, is they are Turing complete. This is not the case, at least not yet. But there's an interesting thing in C#. There's an interesting proposal at the language level, which is called shapes and extensions. If they ever implemented shapes and extensions, they could make this thing awesome. Because this is essentially the underlying mechanics that we are doing by hand now that will implement and give you the ability to do this kind of stuff. It also, these kind of techniques can be used to devirtualize. While CoreCLR, the new CoreCLR version from 2.0 and forward has the ability to devirtualize in some specific cases, for the difficult cases that the just-in-time compiler is not able to work with, you can still use these kind of techniques. So if your problem is, how do I deal with virtual codes, that it can happen on highly efficient code, is you go this route. Also, hiding pointers and references. This is big. You can actually treat a pointer or a managed reference as the same thing. You don't need to know how it was implemented. This is like in the old books saying, I have an opaque reference. This is like the starting of the type system theory. Is I have an opaque reference, I don't care what is inside. Because I have the tools to actually call and modify the state of that reference without knowing what is backing it. You can actually also build indexers. And the cost of that abstraction is a long. An actual long on the stack. So it also allows you to avoid lambda context capture. Because if you have an indexer that you can put on top, you just pass the index. You just make sure that you make that information available in some backing store, which is the thing that you are passing around through your chain of methods, your context. And because you are passing this interface that behaves like a long, but actually from the point of view of your code is very meaty, is an opaque reference, Now the cost of lambdas is essentially 0. These kind of things can actually cut down on your allocations very hard. And one final thought, and this is general, this is not C#, this is general. If you are working on code and you're optimizing, and you have people that is optimizing your code, one thing that I like to say about optimizing code, if you are not doing, you're essentially burning money, like old style burning money. But whenever you start this, if you are someone that is not new to performance, you are going to go follow the route, go for the bottlenecks. If management says no to higher risk, no, we have to rebuild this, makes sense. Okay, let's go to the next level. If the cost is still too high or the risk is still too high, then figure out what are the worst places and let's go and fix it. Let's figure out where the 0.88 is. But the problem is that when you are done, you are not done. And this is what I wanted to convey. Your bottlenecks never, ever go away. They just become more insidious. Because now what used to be a bottleneck and you fix it like in 2 months and you were like, hey, this is great. Now your next bottleneck is going to be an order of magnitude complex. So instead of 2 months, it's really going to cost you 6 or a year. So what I mean here is when you are arriving to the point that your software is actually efficient, you are going to end up dealing with stuff like the memory model, how this executed on the CPU, and that kind of stuff, which for some people like me is fun, but for most people is like, where do I go? I want to quit. But anyway, so just to give you an idea, we are in the 4.0 version, and we already know that we have to get rid of our JSON parser, which is state-based. And the bad news is that the new core CLR parser, which is going to be very fast, is not going to cut it for us because it's still a state machine. We need to go to streaming, so we have to build it ourselves again. And the other one is our indexing engine that we have been known for a fact that it was a problem back in 3.0, but wait, from all the problems that we had, it was like, okay, yes, we have this. Rebuilding this will take us another 2 years. We're not going to delay. So we went first for one, and now we are going for the other one. But just to give you an idea, the entire database allocation budget for almost anything is below 500 megabytes. A single indexing run of Lucene cost me 10 gigabytes. So if I take a like 10-minute footprint of all the memory allocations, it's like Lucene, JSON on like the 10th. And if we are talking about gigabyte, megabyte, hey, 100. Just to give you an idea of how complex the thing becomes. Thank you all for coming, and if we have some time, we can have some questions.